An extraterrestrial entity is altering its trajectory, and humanity could be its intended destination. 3I Atlas, an object previously believed to be a mere celestial wanderer from beyond our solar system, has begun a subtle yet consistent acceleration in a direction that defies conventional astrophysical understanding. Independent analyses, building upon Avi Loeb's findings of a non-gravitational impetus near perihelion, suggest that if this acceleration persists for a mere 50 days, its speed could increase by 86 meters per second. Such a change would precisely align its path with Earth on December the 19th, 2025. The critical question remains: is this a consequence of natural physics or deliberate propulsion? Is it a chance confluence of solar radiation and cosmic dust, or a meticulously planned maneuver? Concurrently with this perplexing motion, a distinct frequency of 1.44 gigahertz has been detected. These faint, rhythmic, almost mathematically patterned pulses echo through the vastness of space, bearing an uncanny resemblance to a response. Could this indicate a form of coordination? Remain engaged, for by the conclusion of this exposition, you will grasp why leading scientific minds are contemplating the extraordinary. 3. Atlas is not merely passing through. It may be actively steering towards us. If this enigma continues to captivate you as it has me, please honor this channel with a like and subscribe to ensure you receive every update as this unfolding narrative progresses in real time. Share your thoughts in the comments, indicating your location, the current time there, and your perspective on this developing situation. To foster the growth of this intellectual community, consider disseminating this video across platforms such as X, Facebook, Reddit, or even within your personal messaging groups. Your engagement is what empowers us to pursue and deliver stories of this magnitude. Therefore, thank you for your unwavering support. Part 1. Unveiling the assertion. Something is approaching. Presently, amidst the expanse between Mars and Jupiter, a visitor originating from another stellar system is traversing our celestial neighborhood. This is not conjecture. It transcends the realm of science fiction. The entity is a verifiable phenomenon, identified as 3I Atlas. It was initially catalogued on the 1st of July, 2025, by the Asteroid Terrestrial Impact Last Alert System, an observatory situated in Chile. What elevates this celestial body beyond the ordinary is not solely its interstellar provenance. Its present activities are what render it truly remarkable. A series of communications emerged on X, the digital forum formerly recognized as Twitter. An independent investigator presented calculations that arrested the attention of many. The core assertion is as follows. Should 3I Atlas maintain a non-gravitational acceleration approximating 0.02 millimeters per second squared for approximately 50 days, it could achieve a velocity modification of around 86 meters per second. This calculated alteration in velocity, according to the claim, possesses the potential to synchronize its trajectory with Earth's orbit by around December the 19th, 2025. To reiterate, it could align with Earth. The published statements extended further, postulating that this was not a fortuitous alignment. They characterized it as a deliberate act of navigation. The communication even alluded to 1.44 gigahertz transmissions, suggesting potential dialogue or course adjustments, a reciprocal exchange between an advanced probe and a source within proximity to Mars. Before dismissing this as mere speculative theory, let us consider the established facts. The object's existence is confirmed. Its orbital path is hyperbolic, signifying that it is not gravitationally bound to our Sun. It originated from the vast expanse between stars. Its closest proximity to the Sun, known as perihelion, occurred around October the 30th, 2025. Furthermore, there are indeed documented instances of non-gravitational acceleration. This indicates that the object is exhibiting motion that cannot be attributed solely to gravitational forces. Non-gravitational acceleration is not an inexplicable phenomenon. It is a manifestation of physical principles that, in this particular context, we are still endeavoring to fully comprehend. When a celestial body deviates from a trajectory predicted by gravitational laws, an external force is at play. Typically, this force arises from outgassing. Comets frequently exhibit this behavior. The sublimation of ice transforms into vapor, expelling gas in jets that impart a minute impulse to the object. A force of 0.02 millimeters per second squared may seem negligible. It is roughly 150,000th of Earth's gravitational pull. However, within the vacuum of space, over extended periods of days and weeks, even these minuscule impulses can accumulate into a significant effect. Herein lies the captivating aspect. This marks only the third verified interstellar object ever detected. The first was Oumuamua in 2017, the enigmatic cigar-shaped anomaly that fueled extensive debate. The second was Borisov in 2019, which presented as a conventional comet. Now we have 3I Atlas, and unlike its predecessors, this object is displaying characteristics that provoke profound and unsettling inquiries. What are the implications? If this is simply an unusual comet, it still holds considerable scientific value, offering a glimpse into the formation of planets in distant star systems as it traverses ours. However, if the acceleration is purposeful, if some intelligence is guiding this object, then we are contemplating an event of an entirely different magnitude. We are considering the remote but distinct possibility of an artificial construct originating from an alien civilization. The objective of this inquiry is straightforward. We shall meticulously examine the assertion. We will scrutinize the accompanying data, the underlying assumptions, the mathematical computations, and the speculative extrapolations. We will delineate between established knowledge and informed conjecture. Furthermore, we will look ahead to the events anticipated in late 2025 and early 2026, a period when observational data may either substantiate or definitively refute this hypothesis. This endeavor is not about propagating fear. It is about discerning what is factual, what is plausible, and what is merely unsubstantiated chatter. The reality is that the cosmos is replete with phenomena yet to be understood. Periodically, an object emerges that challenges our established models. 3I Atlas might represent such an instance, or it could be a perfectly conventional interstellar comet exhibiting outgassing in a manner that appears anomalous to us. By the conclusion of this presentation, you will be contemplating a pivotal question. Is it a natural comet, an extraterrestrial probe, or something in between? You will possess the tools to form your own informed judgment, understanding the scientific principles, the mathematical frameworks, the observational strategies, and the broader ramifications. You will also know what to monitor in the ensuing months. This exploration is structured across 3 acts. Act 1 will meticulously present the assertion and the supporting data. We will investigate the nature of 3I Atlas, analyze the empirical evidence, and scrutinize the assumptions underpinning the Earth intercept scenario. Act 2 will delve into more speculative interpretations, address the controversies, explore natural versus exotic explanations, and examine the social media narratives that have amplified this story. Act 3 will broaden our perspective to encompass recent advancements in space science, artificial intelligence, and radio astronomy, forging connections between 3I Atlas and the forefront of scientific discovery. Finally, we will conclude with an outlook on future developments and guidance on what to observe. One final consideration before we proceed. The universe operates with an indifference to our comfort. It does not concern itself with our preparedness for its revelations. For the vast majority of human history, we adhered to the belief that we were singular. We presumed Earth to be the epicenter of all existence, with the cosmos revolving around us. Every significant discovery since that era has served as a lesson in humility. We ascertained that Earth orbits the Sun. We learned that our Sun is but one among billions. We discovered that galaxies extend beyond enumeration. Now we are learning that objects from other star systems can indeed visit us. What transpires when one of these interstellar travelers exhibits behavior that defies easy explanation? Next, we will examine the empirical data to enable you to independently assess whether this claim holds water or dissipates under scrutiny. Part 2. The factual evidence. The discovery of 3I Atlas transpired on the 1st of July, 2025. The Asteroid Terrestrial Impact Last Alert System, a constellation of telescopes in Chile tasked with identifying near-Earth objects, registered an unusual detection. Initially, it appeared as an unremarkable faint point traversing the night sky. However, subsequent orbital calculations revealed something extraordinary. The trajectory was hyperbolic. A hyperbolic trajectory signifies that the object is not gravitationally tethered to our Sun. Its velocity is too great to be ensnared by solar gravity. It originated from an external region, transited our solar system, and will eventually depart, venturing back into the interstellar void. This is the definitive characteristic of an interstellar visitor. The designation 3I was subsequently assigned, marking it as the third confirmed interstellar object. Let us now consider its orbital parameters. Perihelion, the point of closest approach to the Sun, occurred around October the 30th, 2025. The distance at this point was approximately 1.36 to 1.4 astronomical units. An astronomical unit is defined as the average distance between Earth and the Sun, equivalent to about 150 million kilometers. Thus, at perihelion, 3I Atlas was situated between approximately 203 and 210 million kilometers from the Sun, placing it roughly within the orbital path of Mars. Its closest predicted approach to Earth is slated for December the 19th, 2025. The calculated distance is approximately 1.8 astronomical units, roughly 268 to 270 million kilometers. To provide context, the Moon is situated about 384,000 kilometers from Earth. This object will pass at a separation equivalent to approximately 700 times the Earth-Moon distance. This is a considerable distance, far removed from any conventional definition of a near miss. Now let us address the anomaly. In a publication on Medium, Avi Loeb, the noted Harvard astrophysicist, recognized for his research on Oumuamua and the search for extraterrestrial intelligence, reported an unusual observation. Astrometric data, obtained from the Jet Propulsion Laboratory and the Atacama Large Millimeter Array, indicated a deviation from its predicted trajectory. The object was not positioned where gravitational forces alone would dictate. The discrepancy amounted to approximately 4 arc seconds. While a minute angular shift, it is nonetheless significant when tracking an object across vast cosmic distances. Loeb calculated a non-gravitational acceleration of approximately 0.02 millimeters per second squared. He then employed a momentum conservation equation to investigate potential causes. If outgassing is the driving mechanism, meaning jets of vapor propelling the object, then the rate of mass loss would need to be substantial. His calculations indicated that at least 1/16 of the object's mass would require sublimation over a period of roughly 1 month to generate such an acceleration. Let us pause to consider this. While outgassing is a natural phenomenon, the scale suggested here is noteworthy. Comets regularly experience outgassing. When ice transitions directly from solid to gaseous form, it is expelled from the surface, generating thrust. This is akin to a weak but measurable rocket effect. The challenge with 3I Atlas lies in the magnitude. If the object possesses the mass suggested by some estimations, in the tens of billions of tons, then shedding 1/16 of that mass within a single month should manifest as a conspicuous plume of gas and dust, a visible coma, and a tail, observable phenomena. Visually, 3I Atlas has exhibited certain atypical characteristics. Imagery reveals a discernible jet structure, possibly directed towards the sun rather than away from it, which is an unusual configuration. The coloration of the object has also attracted attention. Reports describe it as possessing a bluer hue than the sun, potentially indicating the presence of ionized carbon monoxide rather than conventional dust. These observations are suggestive, but not definitively conclusive. Comets can exhibit peculiar behaviors, and interstellar comets even more so. What does the data not reveal? Loeb himself does not assert that the object is on a trajectory that would result in an Earth intercept. He also does not claim it is deliberately maneuvering towards our planet. The data confirm an acceleration and an observed positional offset, suggesting an intriguing phenomenon is occurring. The leap to an Earth intercept scenario and the interpretation of intentional steering originate from external sources. It stems from social media posts that utilized Loeb's quantitative findings to conduct further calculations. Here is a critical distinction. The empirical data are provocative, but not inherently inexplicable. We are observing a hyperbolic interstellar object, exhibiting some degree of outgassing and a jet structure that falls within the purview of established physics. While it is certainly unusual, it is not impossible. The central question is whether the existing data support the bold claim that 3I Atlas is actively altering its course toward Earth, or if real data have been augmented with layers of assumption to arrive at a dramatic conclusion. To date, what we possess is the following: a confirmed interstellar object, a trajectory that brings it into relative proximity with Earth, albeit still at a considerable distance, a non-gravitational acceleration that could be attributed to outgassing or an alternative cause, and a mathematical calculation demonstrating how a modest, sustained impulse over 50 days could result in a significant velocity change. Is this sufficient to declare that the object is aligning with Earth? This is the question we will tackle next by examining the mathematical underpinnings and the assumptions that transform raw data into a compelling narrative. Part 3. Extrapolation to Earth intercept, mathematics and assumptions. Let us perform the arithmetic. The assertion originating from social media commences with a fundamental equation from classical physics. Acceleration multiplied by time equals the change in velocity. If an object experiences a constant acceleration of 0.02 millimeters per second squared and sustains this for 50 days, what is the resulting change in velocity? 50 days equates to 4,320,000 seconds. Multiplying this by 0.02 millimeters per second squared, which is equivalent to 2 times 10 to the power of -5 meters per second squared, yields approximately 86.4 meters per second. This is the delta V, the alteration in velocity. The mathematical calculation is accurate. There is no disagreement regarding the arithmetic itself. Now let us consider the displacement. When a constant acceleration is applied over a duration, it not only modifies velocity but also alters position. The displacement under constant acceleration is calculated as 1/2 multiplied by acceleration multiplied by time squared. Substituting the numerical values, 1/2 multiplied by 2 times 10 to the power of -5 meters per second squared, multiplied by 4.32 times 10 to the power of 6 seconds squared, results in approximately 1.87 times 10 to the power of 8 meters. This equates to 187,000 kilometers, roughly half the distance from Earth to the Moon. Therefore, yes, the numerical values are substantial. A minor yet continuous thrust applied over 50 days could shift an object's path by hundreds of thousands of kilometers. Within the framework of orbital mechanics, this is a significant effect. It could alter the location and timing of an object's passage through a specific plane. It could modify the closest approach distance. It could theoretically transform a distant flyby into a closer encounter. However, this is where assumptions begin to accumulate. The calculation presumes that the acceleration remains uninterrupted for the entire 50-day period. Is this assumption valid? We cannot ascertain this. The acceleration was measured at a specific juncture near perihelion. Whether it continues for weeks or months remains uncertain. Outgassing typically fluctuates in accordance with an object's proximity to the Sun. As an object moves away from perihelion, solar heating diminishes, leading to a reduced rate of sublimation. Consequently, the thrust might weaken or cease altogether. The calculation also assumes that the acceleration is applied precisely in the correct vector. Direction is as critical as magnitude. If the thrust is oriented laterally relative to Earth's orbit, it might alter the orbital plane but would not significantly impact the closest approach distance. If it is directed prograde, increasing the object's speed, it affects the arrival time. If it is retrograde, reducing its speed, the same holds true. If it is radial, pushing towards or away from the Sun, it modifies the semi-major axis and eccentricity. Without knowledge of the acceleration's direction, integrating the velocity change into a trajectory prediction becomes speculative. Timing represents another crucial assumption. The object must apply the thrust at the opportune moment and in the appropriate direction to ensure the resultant path intersects Earth's orbit when Earth is precisely at that location. Earth traverses space at approximately 30 kilometers per second around the Sun, covering immense distances within days. Intercepting a moving target necessitates precise timing and vectoring. A deviation of 187,000 kilometers could alter the point of intersection. However, if Earth is not present at that exact moment, the intercept will not occur. Then there is the matter of energy requirements and mass. If the object possesses the mass suggested by estimates, tens of billions of tons, sustaining a continuous thrust demands prodigious amounts of energy. If it is natural outgassing, the rate of mass loss must be substantial, as calculated by Loeb. If it is artificial, it implies a propulsion system capable of prolonged thrust. Both scenarios strain credulity without supporting evidence. Finally, we must consider the influence of perturbations. Space is not devoid of external forces. Solar radiation pressure, the gravitational pull of planets, solar wind, and even the Yarkovsky effect can all influence the trajectory of a small body. The simplistic calculation assumes these factors are negligible or tend to average out. In reality, however, they introduce variability and uncertainty. A purely deterministic 50-day thrust period is an idealized scenario. Allow me to offer an analogy. Envision yourself driving on a highway. You are aware that you can accelerate to a speed 60 kilometers per hour faster than your current velocity. This is akin to knowing your delta V. However, merging into the correct lane at the opportune moment to reach a specific exit requires more than just speed. You must ascertain the exit's location, the speed of surrounding traffic, the optimal time to accelerate, and the precise direction to steer. The arithmetic of velocity change is one aspect. The geometry and timing involved in orbital mechanics constitute another. The extrapolation derived from social media assumes that the acceleration was directed in a manner beneficial for an Earth alignment. We lack definitive evidence for this. The data indicate some acceleration, but not its vector in relation to Earth's orbit. The assertion further includes the claim, this acceleration is purposeful and Earth-targeting. This represents an interpretation superimposed upon the data, rather than a derivation from it. Here is what we know versus what is assumed. We know that a non-gravitational acceleration is occurring. We know it is minute but measurable. We know the object's orbit will bring it into relatively close proximity to Earth in December. We assume the acceleration will persist for 50 days. We assume it is directed appropriately. We assume the timing will align. We assume no other factors will intervene, and we interpret all of these conditions as deliberate maneuvering towards Earth. Each assumption forms a link in a chain. If even one link breaks, the entire claim disintegrates. The pertinent question is not whether the mathematics are correct. They are. The question is whether the real-world conditions conform to these assumptions. Next, we will examine the actual trajectory and closest approach distance to determine if a shift of 86 meters per second could realistically transform a 270 million kilometer flyby into something more concerning. Part 4. Object trajectory and missed distance. The official figures are unambiguous. According to NASA and the European Space Agency, 3I Atlas is projected to pass Earth at a distance of approximately 1.88 astronomical units on December the 19th, 2025. This translates to roughly 268 to 270 million kilometers. To grasp the scale of this distance, recall that 1 astronomical unit represents the average distance between Earth and the Sun, approximately 150 million kilometers. Therefore, at 1.8 astronomical units, the object will be nearly double Earth's orbital distance at its closest approach. This is not considered close by any standard employed in planetary defense. An object is deemed potentially hazardous if its orbit brings it within 0.05 astronomical units of Earth, approximately 7.5 million kilometers. 3I Atlas will pass at a distance exceeding 30 times that threshold. Both NASA and ESA have explicitly stated that the object poses no threat to Earth. So, how are missed distances calculated in orbital mechanics? When an object approaches on a hyperbolic trajectory, its path is dictated by its velocity, direction, and the gravitational influences it encounters. The missed distance essentially represents the closest point of approach, determined by the object's trajectory relative to Earth's position at a specified time. For 3I Atlas, this calculation yields a missed distance of 1.8 astronomical units on December the 19th. Now let us address the central query. Could a velocity change of 86 meters per second significantly alter that missed distance? The answer is contingent upon the context. Yes, in principle, a delta phi of 86 meters per second applied over 50 days could shift the object's trajectory by hundreds of thousands of kilometers. As we previously calculated, the potential displacement could approximate 187,000 kilometers. This is not insignificant. In orbital mechanics, minor alterations in velocity can lead to substantial positional changes over time, particularly when applied early in the trajectory. However, no, transforming a 270 million kilometer miss into an Earth impact would necessitate considerably more than 86 meters per second, unless the vector and timing were exceptionally favorable. The object is traversing space at approximately 60 kilometers per second, or 60,000 meters per second. 86 meters per second represents less than 0.15% of its total velocity. To modify the trajectory sufficiently to reduce the missed distance from 270 million kilometers to zero would require either a substantially greater delta V or an almost perfect alignment of thrust direction and timing. The direction of the thrust is paramount. Imagine the object's trajectory as a line through space. If you apply a force perpendicularly to the velocity vector, you alter the orbital plane. You might shift the path laterally by 100,000 kilometers, but this would not necessarily bring it closer to Earth. If you apply force parallel to the velocity vector, either increasing or decreasing speed, you modify the arrival time. The object may arrive at the plane of Earth's orbit sooner or later. But again, that does not guarantee a closer encounter unless Earth happens to be precisely in that location. When you apply force radially towards or away from the Sun, you modify the orbit's shape, its eccentricity, and the closest point of approach. There is a concept in orbital mechanics known as the B-plane. This is an imaginary plane that is perpendicular to the incoming path, used to determine where an object will intersect relative to a designated target. Consider it akin to a dartboard. Earth represents the bullseye. The object's trajectory pierces this plane at a certain point, and the distance from the bullseye to that point signifies the missed distance. Even a minor alteration in velocity can shift the point where the object crosses the plane. But transitioning from the outer edge of the dartboard to the center demands a very specific impulse. Without knowledge of the direction of 3I Atlas's non-gravitational acceleration relative to Earth's position, we cannot ascertain the actual change in the missed distance. The assertion circulating on social media presumes the impulse is in the correct direction. This is a significant assumption. Furthermore, the object's mass is a factor. Estimates indicate that 3I Atlas is substantial, potentially exceeding 33 billion tons and measuring several kilometers in diameter. Propelling a celestial body of such magnitude is challenging if the mechanism is natural outgassing. It's akin to attempting to steer a mountain by evaporating ice from its surface. If the mechanism is artificial, it implies an engine or propulsion system of immense power. Regardless of the origin, the physics involved presents considerable difficulties. Scientists from NASA and ESA, who have access to comprehensive astrometric data and orbital models, have concluded that the object is not on a trajectory to intersect with Earth. They account for uncertainties, gravitational disturbances, and potential non-gravitational forces. Their models indicate a safe passage. If the data suggested otherwise, even if there were a slight possibility of impact, the alarm systems would be activated. Planetary defense networks are specifically designed to identify and monitor potentially hazardous objects. 3I Atlas is not currently listed as a threat. Therefore, a reality check on the missed distance boils down to this. The alignment of geometry and timing renders an Earth impact scenario highly improbable at this juncture. The object would require a considerably larger velocity change, applied with exceptional precision in direction and at a critical moment, to transform a 270 million kilometer flyby into a dangerous event. The numbers might appear alarming if one focuses solely on the arithmetic of velocity change, but the complete picture, encompassing orbital mechanics, timing, and missed distance, all point towards a distant encounter. This does not imply the object is uninteresting. Far from it. Its non-gravitational acceleration, its unusual characteristics, and the very fact that it is an interstellar visitor all contribute to its scientific value. However, the Earth intercept scenario, the claim that it is aligning with us, remains purely speculative. Next, we will examine the intensifying observational campaign, the telescopes focusing on 3I Atlas, and the verifiable predictions that will soon reveal whether this object is a comet, a probe, or something in between. Part 5. Observational Campaign and Testable Predictions. The ensuing months will be pivotal. Between now and early 2026, 3I Atlas will be subjected to rigorous scrutiny. Telescopes across the globe and in orbit are already tracking its movement. The closest approach to the Sun, known as perihelion passage, occurred around October 30th, 2025. Following this, it is now moving outward, approaching its closest encounter with Earth on December 19th. This period represents the primary observation window, and it is finite. Once the object passes Earth and ventures deeper into the outer solar system, it will become undetectable. The principal instruments participating in this campaign include some of humanity's most powerful observational tools. The Hubble Space Telescope is capable of capturing high-resolution images across visible and ultraviolet wavelengths. The James Webb Space Telescope, with its infrared capabilities, can detect thermal signatures and analyze the composition of any surrounding gas or dust. Terrestrial observatories such as the Very Large Telescope in Chile and the KEK Observatory in Hawaii are also contributing. Radio telescopes are actively listening for any unusual emissions. Furthermore, spacecraft in Mars orbit might catch a glimpse as 3I Atlas passes relatively near the red planet. An intriguing coincidence also exists. On November 4th, 2025, the European Space Agency's Jupiter Icy Moons Explorer, designated JUICE, will pass within approximately 64 million kilometers of 3I Atlas. While not sufficiently close for a direct flyby, JUICE's instruments may be able to gather data from this distance. Every piece of information gathered is valuable. Avi and his fellow researchers have outlined predictions that can be tested. These predictions are contingent upon whether the non-gravitational acceleration is attributed to natural outgassing or an alternative cause. If outgassing is the origin, a substantial loss of mass would be expected. Loeb's calculations suggested that at least 1/6 of the object's mass would sublimate over approximately 1 month. This process should generate a considerable cloud of gas and dust, a visible coma, and likely a tail extending behind the object as solar wind disperses the particles. Thus, the initial prediction is straightforward. If the acceleration is natural, telescopes should detect a vast envelope of gas and dust. Spectroscopic analysis should confirm the presence of volatiles such as water, carbon monoxide, carbon dioxide, or methane. The object should exhibit characteristics consistent with a comet, displaying all the telltale signs of sublimation-driven activity. Conversely, if no significant cloud is observed and the mass loss is minimal or absent, the hypothesis of natural outgassing would be weakened. This outcome would be highly significant, suggesting that the acceleration originates from a different source, one that does not necessitate the expulsion of substantial material. In such a scenario, non-natural or technological explanations would gain more plausibility. The measurements requiring close attention include astrometric residuals, which represent the discrepancies between the object's actual position and its predicted position, based on purely gravitational models. These residuals reveal the magnitude and direction of any non-gravitational forces. As more observational data accumulates over the coming weeks, astronomers will refine the orbit and quantify the acceleration with increased precision. Spectroscopy serves as another crucial tool. By dispersing the light emitted by the object into its constituent wavelengths, scientists can identify the present molecules and atoms. 3I Atlas has already been noted for its unusual coloration, described as bluer than the sun. This could be indicative of ionized carbon monoxide, a spectral signature associated with specific types of comets, or it might signify something else entirely. Detailed spectroscopy will provide further insights into its composition and whether it aligns with known cometary chemistry. Imaging is also vital. The morphology of any observed coma or tail, the structure of emanating jets, and the presence of asymmetries all offer valuable clues. Some reports have mentioned an anti-tail, a jet directed towards the sun rather than away from it. While unusual, this phenomenon is not unprecedented. Comets occasionally exhibit features pointing forward due to observational geometry or rotation. High-resolution images will clarify whether these observations are consistent with natural processes. Additionally, radio astronomy is playing a role. Social media posts have alleged that the object emitted 1.4 gigahertz pings, purportedly communication or course correction signals. This claim is entirely unverified, but radio telescopes will be monitoring regardless. If any unusual emissions are detected, whether at 1.4 gigahertz or any other frequency, they will be captured and analyzed. Radio signals emanating from a comet are rare, but not impossible, typically associated with plasma interactions. However, a strong, structured signal would present a different scenario altogether. The observational campaign faces certain challenges. Timing and geometric alignment are critical around perihelion. During this phase, the object was positioned close to the sun in the sky. making observation difficult due to solar glare. As it moves away from the Sun and towards Earth, visibility improves. However, by late December, following its close approach, it will begin to fade as it recedes from both the Sun and Earth. The observation window is thus quite limited. Factors such as weather conditions, telescope availability, funding, and coordination all influence the process. Not all telescopes can conduct observations every night. The acquired data requires processing, analysis, peer review, and eventual publication. Scientific progress proceeds at a slower pace than the rapid dissemination of information on social media. Claims may spread within hours, but the observational evidence takes weeks or months to confirm or refute. Nevertheless, this is an exciting period. We are observing a visitor from another star system in real time. The same sophisticated telescopes used to study distant exoplanets and analyze the chemistry of alien atmospheres are now focused on an object passing through our own cosmic neighborhood. This represents a rare convergence of opportunity and technological capability. By early 2026, we anticipate having definitive answers. If 3I Atlas behaves as a typical comet, exhibiting significant outgassing, a prominent coma, a tail, and spectroscopic signatures of volatiles, then the natural explanation will prevail. The non-gravitational acceleration would simply be a comet engaging in cometary activities, perhaps with heightened intensity due to its interstellar origin and composition. However, if the observational results indicate minimal mass loss, no substantial cloud formation, and yet the acceleration persists or exhibits directional characteristics inconsistent with jetting, then we will face a scientific conundrum. Not a catastrophe, but a puzzle that does not readily fit our established models. This is when the conversation shifts. This is when exotic hypotheses, which we will explore next, transition from mere speculation to demands for serious scientific consideration. The subsequent phase of this investigation will delve into the debate between natural and non-natural explanations, the influence of social media in amplifying unsubstantiated claims, and the implications if 3I Atlas is found to be something other than a comet. Part 6. Non-gravitational acceleration. Natural explanations. Comets are often described as dirty snowballs, a simplification used in introductory astronomy. The nucleus of a comet comprises a mixture of ice, rock, and organic compounds. When a comet approaches the Sun, solar radiation heats its surface, causing the ices to sublimate, transforming directly from a solid to a gaseous state without an intermediate liquid phase. The escaping gas carries dust particles with it, forming a cloud known as a coma, and frequently a tail that trails away from the Sun. This outgassing process not only creates a spectacular visual display, but also generates thrust. The gas molecules possess momentum. As they depart from the nucleus, they exert a reaction force on the comet itself, akin to a leaky balloon propelling itself around a room. While this effect is subtle, it is measurable and is referred to as a non-gravitational force. Astronomers have been detecting and modeling this phenomenon for decades. Therefore, when Avi reports a non-gravitational acceleration of 0.02 millimeters per second squared for 3I Atlas, the initial presumption is that it is attributable to outgassing. This is the default hypothesis, the most straightforward explanation. However, the specifics are important. Lowe employed a momentum conservation equation to estimate the mass loss required to produce this acceleration. The underlying principle is straightforward. The force acting on the comet is equal to the rate of mass loss multiplied by the velocity of the outflowing gas. Force equals mass times acceleration. Rearranging this equation allows us to determine the mass loss rate. If the outflow velocity is a few hundred meters per second, typical for cometary jets, and the acceleration is 0.02 millimeters per second squared, we can calculate the rate at which the comet is losing mass. The result is striking. If 3I Atlas possesses a mass of approximately 30 billion tons, the calculation suggests it would need to lose roughly 5 billion tons per month to sustain this acceleration. This equates to about 1/6 of its total mass within a 30-day period. Over several months, the comet would effectively evaporate a significant portion of itself. This represents a substantial mass loss, which should be visually apparent. Astronomers would expect to observe a vast coma, an extensive cloud of gas and dust enveloping the nucleus. The tail should be prominent, and spectroscopic analysis should reveal an abundance of volatiles. Yet, the observations conducted thus far indicate a more subtle phenomenon. There have been reports of a jet directed towards the Sun, and the object's color is unusually blue. However, a giant coma commensurate with this level of mass loss has not yet been definitively observed. This does not invalidate the natural explanation entirely. Comets exhibit variability. Outgassing can occur episodically, driven by rotation, the exposure of fresh ices, or the collapse of surface layers. It is possible that the high mass loss rate was transient, a burst of activity near perihelion that has since subsided. Alternatively, the gas might be escaping through a concentrated jet rather than dispersing uniformly, rendering the coma less discernible from Earth. It is also conceivable that the composition of the gas is such that it is transparent or carries minimal dust, thus reducing its visibility. The blue coloration, exceeding that of the Sun, is particularly intriguing. It may point to ionized carbon monoxide, a molecule that can dominate the spectral output of certain comets. Carbon monoxide ice is more volatile than water ice, sublimating at lower temperatures and greater distances from the Sun. An interstellar comet, having formed in a different stellar environment, might possess a distinct composition, richer in carbon monoxide or other unusual ices, compared to comets originating within our solar system. Some images appear to show what might be an anti-tail, a feature extending towards the Sun rather than away from it. This is a rare occurrence, but not impossible. It can arise from the geometry of observation, where we view the comet from an angle that makes dust within its orbital plane seem to point forward. Alternatively, it could represent a genuine forward jet, driven by rotational forces or localized heating. The natural explanation necessitates that all these elements align coherently: substantial mass loss, atypical composition, intermittent outgassing, and geometric influences. It presents a complex scenario, but comets themselves are inherently complex entities. They do not all behave uniformly. An interstellar comet, originating from another star system with differing conditions, could readily deviate from the patterns observed in solar system comets. The object's dimensions and mass are also significant considerations. Estimates suggest a diameter of at least several kilometers, potentially 5 or more, and a mass exceeding 30 billion tons. This classifies it as a very large comet. Accelerating a body of such immense mass through outgassing demands considerable energy and material expenditure. It is analogous to attempting to propel a cargo ship by jettisoning its cargo. While feasible, It requires the rapid disposal of a substantial quantity of cargo. Analogies can be helpful here. Imagine a massive container ship losing half its cargo over a month to achieve a modest increase in speed. This is conceivable, but it would be a dramatic event, and one would expect to see containers dispersed widely. Debris fields, evidence of such a loss, would be expected. Similarly, if 3I Atlas is losing 1/6 of its mass within a month, we should observe tangible evidence, such as gas, dust, or a luminous envelope. What would constitute confirmation of the natural explanation? The detection of a large coma, consistent with the projected mass loss rate. Spectroscopic analysis, confirming the presence of water, carbon monoxide, carbon dioxide, or other volatiles in the anticipated quantities. Imaging revealing a classic cometary structure, possibly including a tail and multiple jets. Crucially, the acceleration should exhibit a correlation with the comet's distance from the Sun. As the solar heating diminishes, outgassing should weaken, and the acceleration should decrease. If this does not occur, if the acceleration persists, or even increases as the comet moves farther from the Sun, it would be a significant red flag. Currently, the natural outgassing hypothesis is plausible, but presents significant challenges. The required mass loss rate is exceptionally high, and the observational evidence remains ambiguous. The object's considerable size and mass further complicate the narrative. However, comets have surprised us in the past. Oumuamua astonished us with its acceleration and elongated form. Borisov surprised us by appearing entirely conventional. 3I Atlas might simply be the next surprise, a comet exhibiting extreme characteristics that push the boundaries of our current understanding of typical cometary behavior. Or it could indeed be something entirely different. This is the subject we will explore next: the exotic technological hypotheses that reside at the intersection of speculation and scientific inquiry. Part 7. Non-gravitational acceleration, exotic technological hypotheses. What if the observed acceleration is not a natural phenomenon? What if 3I Atlas is not merely a comet exhibiting unusual behavior? What if it is something artificial, something deliberately dispatched, something engineered? Avi and his colleagues have published a paper titled, "Is the Interstellar Object 3I Atlas Alien Technology?" This is not a facetious inquiry, but a serious scientific investigation framed within the parameters of what can and cannot be definitively ruled out. The paper explores the possibility that the object is a manufactured artifact, potentially a probe from an extraterrestrial civilization. What factors contribute to such a suggestion? Several elements converge. Firstly, the non-gravitational acceleration. If it cannot be explained by outgassing, or if the outgassing explanation strains credulity due to the immense mass loss rate required, then alternative mechanisms must be considered. Secondly, the estimates regarding the object's size and mass. A large, massive object experiencing measurable acceleration implies a significant transfer of energy and momentum. Thirdly, its trajectory. Loeb has noted that the object's path through the inner solar system, its timing, and its alignment with Earth's orbital plane are statistically uncommon. While not impossible, these circumstances are unlikely if it were a random visitor from interstellar space. The energetic considerations warrant detailed examination. For an object with a mass in the tens of billions of tons to maintain an acceleration of 0.02 millimeters per second squared for an extended period of weeks requires a substantial thrust. Using the formula force equals mass times acceleration, and plugging in 10 to the power of 13 kilograms and 2 times 10 to the power of -5 meters per second squared, we arrive at a force of approximately 200,000 newtons. This is equivalent to the sustained thrust of a small rocket engine. However, solar sails are only efficient if they are exceptionally large and highly reflective. Calculations suggest that a sail large enough to accelerate this mass would need to span kilometers and be precisely oriented. Alternatively, it could involve a more advanced technology, such as an ion drive, a fusion engine, or a propulsion system yet to be invented. The 1.4 gigahertz pings mentioned in social media reports add another layer to this hypothesis. 1.4 gigahertz holds significance in the search for extraterrestrial intelligence because it corresponds to the hydrogen line, a natural radio frequency emitted by neutral hydrogen atoms. This frequency is sometimes referred to as the water hole in radio astronomy, representing a relatively quiet band in the electromagnetic spectrum through which signals could propagate across space with minimal interference. If an advanced civilization intended to transmit a signal, 1.4 gigahertz would be a logical choice. However, a critical issue arises. There is no publicly verified detection of such pings originating from 3I Atlas. Radio telescopes continuously monitor the sky, and if a strong, structured signal were emanating from the object, it would have been detected. This claim remains unsubstantiated, residing within the realm of speculation. Nevertheless, let us entertain the hypothesis. Assuming 3I Atlas is an artificial probe, what might be its purpose? Reconnaissance or observation? It might have been drifting through space for millions of years, a remnant of a long-extinct civilization, still fulfilling its programmed mission to survey star systems. Alternatively, it could be actively engaged, deliberately adjusting its course to study interesting celestial bodies. Could it intentionally alter its path to intercept Earth? The concise answer is yes, provided it possesses the necessary capability. A probe equipped with a functional propulsion system could, in principle, modify its trajectory. However, the velocity change required to transform a 27 million kilometer miss into an actual intercept far exceeds 86 meters per second. It would necessitate velocity adjustments on the order of kilometers per second, applied with precise timing and direction. This implies a considerable and sustained thrust over an extended duration. Loeb has also discussed the dark forest hypothesis in relation to 3I Atlas. The dark forest concept, popularized by science fiction author Liu Cixin, posits that the universe is teeming with civilizations, but they remain silent to avoid detection by potentially hostile neighbors. Revealing one's presence could invite destruction, leading all civilizations to remain hidden within the cosmic dark forest, communicating only when absolutely necessary. Loeb suggests that if 3 Atlas is indeed a probe, its actions might indicate a cautious strategy, opting for distant observation instead of direct interaction. This perspective is highly speculative, built upon a series of nested assumptions. The initial assumption is that the object's acceleration is not a natural phenomenon. The second assumption is that this acceleration is artificial. The third posits that it is controlled by an intelligence. The fourth assumes this intelligence exhibits caution or specific intent in its approach toward Earth. Each successive assumption progressively diminishes the likelihood of the entire scenario. What might serve as definitive proof of a technological origin? Several possibilities come to mind. Unexpected radio transmissions, particularly those exhibiting structured patterns and informational content. Sustained thrust signatures that imply constant acceleration without a corresponding loss of mass or expulsion of gas. Remarkably low mass loss accompanying high acceleration, which would contravene the fundamental principles of rocket propulsion unless an external energy source is involved. Highly reflective surfaces suggesting manufactured materials rather than natural rock and ice, and alterations in attitude or orientation that cannot be explained by simple rotational motion. Should observations reveal any of these indicators, the conversation would shift dramatically. Suddenly, the unconventional hypothesis would transition from fringe speculation to a plausible explanation warranting thorough investigation. However, if none of these characteristic signatures manifest and the object continues to behave like an unusual but natural comet, then the technological hypothesis would recede back into the realm of the unlikely. The implications are profound. If the probe scenario holds true, it would definitively confirm humanity's solitude is not absolute. It would signify that another civilization has achieved a technological level, capable of dispatching objects across interstellar distances. This would inevitably lead to questions about their motivations, their longevity, and their ultimate fate. Are they still present in the cosmos? Did they dispatch a single probe or a multitude? Is 3 Atlas an ancient artifact or a recent creation? Nevertheless, the magnitude of the potential discovery does not inherently validate the hypothesis. Extraordinary claims necessitate extraordinary evidence, and currently, the evidence is, at best, ambiguous. The observed non-gravitational acceleration is a verified phenomenon, but its origin remains uncertain. The trajectory, while unusual, is not entirely outside the realm of possibility for a random interstellar object. The purported radio pings lack verification. The absence of a substantial coma is suggestive but not conclusive. Scientific progress relies on the rigorous testing of hypotheses, the formulation of predictions, and their subsequent validation against observational data. The technological hypothesis also generates specific predictions. The absence of a large gas cloud due to a lack of outgassing, persistent acceleration independent of solar proximity, implying a propulsion system not reliant on the sun, and the potential for radio emissions or other non-thermal signatures. Over the ensuing months, observational data will be crucial in testing these predictions. Should the object prove to be a natural phenomenon, humanity will still have gained valuable knowledge, pushing the frontiers of cometary science, exploring the chemistry and dynamics of interstellar visitors, and refining our models against an exceptional case. If, however, the object is determined to be artificial, it would represent the most significant discovery in human history. In either outcome, the observations anticipated in late 2025 and early 2026 promise to be captivating. We now turn our attention to the dissemination of this narrative, examining how social media transformed scientific data into a story of alien interception and conspiracy. Part 8. The Social Media Narrative and Conspiratorial Framing. The posts began appearing on X in mid-October 2025. An independent researcher, unaffiliated with any major institution, presented a series of assertions. The central claim was straightforward. 3 Atlas is accelerating. If this acceleration of 0.02 millimeters per second squared were to persist for 50 days, it would result in a velocity increase of 86 meters per second. Such a change in velocity, if applied in the correct direction at the opportune moment, could align the object with Earth by December 19, 2025. Subsequently, the claims escalated. The researcher proposed that the acceleration was not incidental, but intentional, suggesting the object was actively maneuvering, correcting its course, and steering itself towards Earth. Furthermore, there were mentions of 1.4 gigahertz pings detected near Mars, purportedly communications, a form of acknowledgement between the object and another entity. The narrative thus shifted from an intriguing scientific anomaly to a more alarming proposition: an alien probe targeting our planet. Let us dissect this piece by piece. The data concerning the acceleration is indeed accurate, as reported by Avi Loeb, and is based on astrometric observations from reputable sources. The calculation that 0.02 millimeters per second squared, multiplied by 50 days, equals 86 meters per second is also correct, representing basic physics without error. However, the subsequent assumptions introduce uncertainty. The assumption that the acceleration will continue for precisely 50 days, that it is directed towards Earth, and that the timing will align perfectly with Earth's orbital position are all unverified. These are extrapolations, mere guesses derived from limited information. The interpretation that the object is positioning itself to intercept Earth is where objective data ends and narrative begins. The implication of alignment suggests intent, an assertion that the object is deliberately navigating towards our planet, for which there is no evidence. The projected missed distance remains at 270 million kilometers, and NASA has indicated no threat. The orbital geometry does not support an intercept scenario, unless a confluence of multiple improbable factors occurs. The 1.4 gigahertz pings are unverified. No major observatory has confirmed any radio emissions from 3 Atlas. If such a signal were present, radio astronomers would be intensely focused on it. While the lack of confirmation does not definitively disprove the pings, it means they cannot be considered credible without supporting evidence. So, how did this narrative gain such traction? Social media thrives on ambiguity and drama. A scientific anomaly, a gap in our understanding, becomes fertile ground for conjecture. Individuals take the available data, overlay their own interpretations, and construct compelling stories. These narratives propagate far more rapidly than the scientific explanations. Because they are inherently more sensational, an alien probe targeting Earth makes for a far more captivating headline than a comet exhibiting unusual outgassing. The underlying psychology is fascinating. Humans possess an innate drive to identify patterns, often perceiving connections where none exist. We are drawn to narratives that imbue order into chaos. An interstellar object displaying anomalous acceleration is not merely an odd comet. It is interpreted as a sign, a message, perhaps even a warning. This interpretation resonates with broader cultural anxieties concerning the unknown, the vastness of space, and the potential implications of contact. Conspiratorial framing intensifies this effect. Once the notion that the object might be artificial is introduced, every ambiguity becomes perceived as corroborating evidence. The absence of a visible coma is deemed proof it is not a comet. Its unusual coloration suggests manufactured materials. Its trajectory implies deliberate targeting. And the lack of official confirmation regarding the radio pings is interpreted as a cover-up. Consequently, the narrative becomes self-sustaining and resistant to refutation. This phenomenon is not unique to 3 Atlas. Objects like Oumuamua underwent a similar cycle. An unusual object is detected, scientists acknowledge their incomplete understanding, and the Internet fills the void with extraterrestrial explanations. Occasionally, scientists themselves, like Loeb, contribute to the speculative discourse by publicly advocating for the consideration of all possibilities, including technological origins. While such openness is valuable in scientific inquiry, it can also fuel sensationalism. Mainstream media outlets often amplify these stories, frequently in simplified or exaggerated forms. Headlines proclaiming an alien probe become common, even when the accompanying article presents a more nuanced perspective. The New York Post, for instance, published an article quoting Loeb concerning 3 Atlas, framing it as a potential alien propulsion system. This framing is crucial, as most readers do not progress beyond the headline, absorbing the idea that scientists suspect alien involvement, and thus that becomes the accepted narrative. The responsibility in science communication lies in clearly distinguishing between what the data demonstrably show and what is being extrapolated from it. The data unequivocally indicate a non-gravitational acceleration, and that is the extent of the factual observation. The subsequent extrapolations, an Earth intercept, intentional maneuvering, and alien technology, are interpretations layered upon the data. While these interpretations might eventually prove true, they are not established facts. A delicate balance must be struck. On one hand, possibilities should not be prematurely dismissed. Scientific advancement often arises from exploring seemingly improbable ideas. On the other hand, speculation should not be equated with evidence. The assertion that 3 Atlas is aligning with Earth does not carry the same weight as the observation of its non-gravitational acceleration. One is measured, the other inferred. Social media tends to collapse this distinction, presenting all information as claims, theories, or possibilities. This degrades the signal-to-noise ratio, leading to debates about the object's threat level, without a consensus on the fundamental data. Misinformation proliferates not necessarily through deliberate falsehoods, but because the boundary between data and interpretation becomes blurred. This leads to a meta-question. Are we adequately prepared for the potential realities? What if the object is natural yet genuinely peculiar, pushing the boundaries of cometary physics? What if it is artificial, confirming the existence of extraterrestrial intelligence? How, as a society, do we process information in an environment where truth and speculation coexist seamlessly within our feeds? The social media discourse surrounding 3 Atlas serves as a compelling case study of the intersection between science and narrative construction. The subsequent section will explore the implications if the narrative evolves into reality, if the object indeed performs an unexpected action. Part 9. Worst Case Hypothesis, Interception. Let us engage in a hypothetical exercise. This is scenario analysis, not a prediction. What if all the preceding assumptions were accurate? What if 3 Atlas managed to alter its trajectory sufficiently to intercept Earth? What would the ramifications be? First, let's consider the parameters. Estimates for 3 Atlas's size range from a few hundred meters to several kilometers in diameter. Some calculations, based on its brightness and an assumed albedo, suggest it could be 5 kilometers across or even larger. Its estimated mass exceeds 30 billion tons, potentially more. This represents a colossal object hurtling through space, Interstellar objects travel at immense speeds. Upon entering a solar system on a hyperbolic trajectory, they are not gravitationally bound to the Sun and thus do not decelerate significantly. 3 Atlas is currently moving at approximately 60 kilometers per second, or 60,000 meters per second, which translates to over 130,000 miles per hour. At such velocities, kinetic energy increases dramatically. The formula for kinetic energy is straightforward. Energy equals 1/2 times mass times velocity squared. Using a conservative estimate, let us assume a mass of 30 billion tons, equivalent to 3 times 10 to the power of 13 kilograms. The velocity can be estimated at 30,000 meters per second, a mid-range value. Plugging these figures into the formula, 1/2 times 3 times 10 to the power of 13 times 9 times 10 to the power of 8 yields approximately 1.35 times 10 to the power of 22 joules. To contextualize this energy, 1 megaton of TNT releases about 4.2 times 10 to the power of 15 joules. Dividing the kinetic energy by this value gives us approximately 3.2 million megatons. For comparison, the most powerful nuclear weapon ever detonated, the Soviet Tsar Bomba, had a yield of 50 megatons. This impact would therefore be 60,000 times more potent. The consequences would be unequivocally catastrophic. An object of this magnitude and velocity would penetrate the atmosphere in mere seconds, with insufficient time for deceleration or significant ablation. It would strike the surface at nearly its full velocity, releasing its entire kinetic energy instantaneously. The resulting explosion would dwarf any event in human history, natural or man-made. Firestorms would erupt across continents. The shock wave would flatten everything within hundreds of kilometers of the impact site. Earthquakes of immense magnitude would convulse the planet's crust. If the impact occurred in an ocean, tsunamis thousands of meters high, traveling at jet speeds, would inundate ocean basins, obliterating coastal cities. However, the immediate devastation would only be the precursor. The immense energy released would vaporize the impactor and a vast volume of terrestrial material, ejecting it into the atmosphere. Dust and aerosols would spread globally within days, obscuring sunlight. Temperatures would plummet, photosynthesis would cease, crops would fail, and the ensuing famine would claim more lives than the initial impact. This scenario constitutes an extinction-level event, though not necessarily the annihilation of all life. Earth has endured more severe events, but it would likely result in the extinction of most large animals, including humanity. This situation would be comparable to the impact event that led to the extinction of the dinosaurs 66 million years ago. Now let us consider a less extreme scenario. Suppose 3 Atlas does not strike Earth directly, but passes significantly closer than the predicted 1.8 astronomical units. Imagine it passes within tens of thousands of kilometers, roughly the distance to geostationary satellites. A close flyby would still be a dramatic event. The object's gravitational influence would subtly perturb Earth's orbit, though likely imperceptibly due to Earth's superior mass. However, potential electromagnetic and plasma interactions could be noteworthy. If the object possesses a magnetic field or carries charged particles, phenomena such as auroras, radio disturbances, and even temporary disruptions to satellite communications might occur. There is also the matter of debris. If 3 Atlas is shedding material, either through outgassing or fragmentation, a close flyby could introduce dust and particles into Earth's atmosphere, potentially intensifying meteor showers. Spacecraft, in low Earth orbit, including the International Space Station and other satellites, would face increased risks from impacts. From a scientific perspective, a close flyby would be an unparalleled opportunity. Telescopes would gather data with unprecedented resolution, radar could map its surface, and spectroscopy could provide detailed compositional analysis. If the object were indeed artificial, its manufactured nature would be undeniably evident at such close proximity. However, let us return to the central question. How much delta V would be required to convert the predicted miss into an intercept? The projected miss distance is 270 million kilometers. To close this gap, a substantial trajectory alteration would be necessary. 86 meters per second is insufficient unless the geometry is extraordinarily favorable. Performing a rough estimation, the object's velocity is 60 kilometers per second. A 1% change in velocity, amounting to 600 meters per second, might shift the miss distance by several million kilometers, depending on the direction and timing of the impulse. To alter the miss distance by 270 million kilometers would likely necessitate a velocity change of several kilometers per second, applied over weeks or months and precisely targeted. This is not achievable with an acceleration of 0.02 millimeters per second, squared over 50 days. A significantly stronger acceleration, sustained for a much longer duration or applied much earlier in its trajectory, would be required. The numerical data do not support an intercept scenario based on the reported acceleration. Therefore, while the worst-case hypotheses are terrifying, the chain of assumptions needed to reach them is lengthy and precarious. The object would require a propulsion system capable of generating immense thrust. Its course correction maneuvers would have needed to commence months or years prior, not just near its perihelion. It would necessitate precise knowledge of Earth's position and velocity. Moreover, the energetic requirements remain daunting. If the object were artificial and intentionally targeting Earth, what would its objective be? Observation appears to be the most plausible motive. Why dispatch a probe across interstellar space only to destroy both itself and its target in a collision? A flyby scenario seems more logical, allowing for close-range study of the planet, its atmosphere, its biosphere, and potentially even its technological signatures before continuing its journey. Alternatively, it might not be targeting Earth at all. The trajectory could be coincidental, a consequence of gravitational dynamics within its originating star system. We may be projecting intent onto randomness, discerning patterns where none exist. What monitoring and defense capabilities do we currently possess? Very few. Planetary defense systems, such as NASA's Double Asteroid Redirection Test, DART, are designed for smaller, slower objects detected years in advance. An interstellar intruder traveling at 60 kilometers per second, detected only months before its closest approach, exceeds our current deflection capabilities. Early warning networks are crucial. If an object were detected years in advance, there might be sufficient time to plan a mission, perhaps even to intercept it for study. However, 3 Atlas was discovered in July 2025, mere months before its perihelion and Earth approach, which is insufficient time to initiate a deflection mission. Thus, while the worst-case scenario underscores the need for preparedness, it does not accurately reflect our current situation. The reality, based on all credible orbital calculations, is that 3 Atlas poses no threat. The miss distance is substantial, and its trajectory is well understood. Agencies are monitoring the object, but there is no cause for alarm. Next, we broaden our perspective to consider the wider implications of interstellar objects for planetary defense and the study of extrasolar systems. Part 10. Broader implications for interstellar objects. Planetary defense. 3 Atlas represents only the third confirmed interstellar object ever detected. The first was Oumuamua, discovered in October 2017. The second was Borisov, identified in August 2019. Prior to these detections, there was no direct evidence that objects originating from other star systems visited our own. Now, we possess concrete proof that they do, and likely more frequently than previously assumed. The study of interstellar objects provides an unparalleled window into the universe beyond our solar system. These are fragments of alien worlds, remnants from planetary systems, located light years away, delivered directly to our doorstep. By analyzing their composition, structure, and behavior, we can glean insights into the chemistry and dynamics of star systems we are unlikely to ever visit. Oumuamua presented a unique enigma from its inception. Its elongated form, irregular rotation, and subtle non-gravitational acceleration ignited extensive debate. Was it a comet, an asteroid, or something entirely different? Spectroscopic analysis revealed no coma or tail, indicating no apparent outgassing, yet it accelerated as it moved away from the Sun, suggesting a force beyond gravity was at play. A prominent hypothesis, famously suggested by Avi Loeb, posited it might be a light sail, a thin, reflective sheet propelled by solar radiation. However, the majority of astronomers favored an alternative explanation. An unusual comet, possibly composed of hydrogen ice or nitrogen ice that sublimates without producing a visible cloud. Borisov, in contrast, presented a more conventional profile. It exhibited characteristics typical of a normal comet, complete with a coma, a tail, and spectroscopic signatures of water and carbon monoxide. Its behavior aligned precisely with expectations for an icy body approaching the Sun. In many respects, Borisov's detection was reassuring, demonstrating that not all interstellar visitors are anomalous. Some are simply comets from distant stellar nurseries. 3 Atlas occupies an intermediate position between these two extremes. It displays certain cometary characteristics, but also exhibits anomalies that do not readily fit standard models. Its non-gravitational acceleration appears stronger than anticipated for its size, and its rate of mass loss, if attributed to outgassing, is extreme. Its coloration and potential anti-tail further contribute to its peculiarity. What does this diversity tell us about interstellar objects in general? It underscores their heterogeneity, implying we cannot assume they all conform to the behavior patterns of solar system comets or asteroids. Their composition, structure, and formation histories are likely to vary significantly depending on their origin and the processes that shaped them. The dynamics of interstellar objects also challenge our current understanding. How frequently do they traverse our solar system? From where do they originate? Are they ejected from planetary systems due to gravitational interactions with massive planets? Or are they remnants of star formation, material that failed to coalesce into planets? Current detection rates suggest that interstellar objects pass through the inner solar system more often than previously estimated. With the advent of more powerful telescopes and expanded sky surveys, our ability to detect them is rapidly improving. 3 Atlas was initially identified by the same system tasked with searching for near-Earth asteroids. Future observatories, such as the Vera C. Rubin Observatory, are expected to detect many more such objects, potentially 1 or 2 per year, within the next decade. This evolving landscape has direct implications for planetary defense. While 3 Atlas currently poses no threat, the confirmed passage of extrasolar bodies through our solar system implies that future visitors might approach much closer. Consequently, our capabilities for detection and response must be enhanced. Planetary defense against interstellar objects presents greater challenges than dealing with objects originating within our solar system, for several key reasons, primarily their immense velocity. Interstellar objects travel at significantly higher speeds, measured in tens of kilometers per second, as opposed to the few kilometers per second typical of solar system objects. This situation leaves less opportunity for reaction and makes course correction more challenging. Secondly, its unpredictability is a factor. We don't know the trajectories of these objects until they're already upon us. Celestial bodies within our own solar system follow predictable paths that we can monitor for years. Visitors from outside the solar system materialize suddenly. Thirdly, the windows for observation are limited. They traverse our space rapidly and then vanish from sight. We may have mere months to study them. The design of missions becomes paramount. If we were to detect a compelling interstellar object years before its closest approach, could we dispatch a spacecraft to intercept it? The answer is perhaps contingent on the trajectory and our preparedness. Missions such as the European Space Agency's Comet Interceptor are conceived to respond swiftly to fleeting targets. Deploying more missions like that, strategically positioned in space and awaiting the appearance of a target, could fundamentally transform our capacity to study interstellar visitors. Enhanced radar and optical tracking systems would also prove beneficial. More precise astrometry leads to more accurate orbital calculations, enabling earlier detection of potential threats and a more thorough characterization of intriguing objects. Artificial intelligence can play a crucial role in processing vast data sets, flagging anomalies, and predicting trajectories. Furthermore, there are technological benefits that arise from this research. Modeling objects moving at high velocities deepens our understanding of impact physics, which has applications in fields such as material science and planetary geology. Tracking faint, rapidly moving objects pushes the boundaries of instrumentation and data analysis. These advancements not only serve planetary defense but also benefit the broader field of astronomy. Now let's consider the implications should 3I Atlas turn out to be artificial. The impact on the pursuit of extraterrestrial intelligence would be immense. SETI has spent decades listening for radio signals, searching for deliberate transmissions from other civilizations. However, an interstellar probe, a physical object dispatched across the galaxy, represents a distinct form of communication and exploration. It suggests a civilization that constructed machines, launched them into space, and either still exists or has left these artifacts behind. If 3I Atlas is a natural but unusual object, the implications for solar system formation and exoplanetary chemistry remain significant. It indicates that the diversity of small body physics is greater than we previously understood. It necessitates that our models of comets, asteroids, and planetesimals must accommodate a wider range of compositions and behaviors. Regardless of its origin, 3I Atlas serves as a wake-up call. Whether the narrative concludes with a confirmed comet or a groundbreaking discovery, the object underscores that our solar system is not an isolated entity. The galaxy is vast, teeming with innumerable stars and planets, and the expanse between them is far from empty. Objects drift, collide, escape, and wander. Some of them eventually find their way here. Public fascination with alien probes can galvanize attention and funding for space science. But it also carries the risk of miscommunication. Planetary defense organizations must meticulously manage both data and its dissemination, providing accurate information while acknowledging inherent uncertainties. The boundary between responsible conjecture and sensationalism is a fine one. Scientists like Avi Loeb tread this line deliberately, advocating for an openness to all possibilities. Critics, however, argue that entertaining speculative hypotheses without sufficient supporting evidence erodes public confidence in scientific endeavors. This debate is valuable, reflecting the inherent tension between caution and curiosity, between conservatism and imagination. 3I Atlas, irrespective of its ultimate classification, embodies this tension. Next, we will transition to recent advancements in other areas of space science that bear relevance to this narrative. Part 11. Recent breakthroughs in exoplanet atmosphere imaging. The year 2025 has been exceptionally fruitful for exoplanet research. The James Webb Space Telescope, commissioned in late 2021, has dedicated years to refining its instruments and observing distant worlds. This year, it has captured something extraordinary: detailed molecular signatures within the atmosphere of a Neptune-sized exoplanet orbiting a star 60 light-years away. The planet, identified as K218b, had been studied previously, but JWST's infrared capabilities allowed astronomers to delve deeper into its atmosphere than ever before. The resulting spectrum revealed the presence of water vapor, methane, carbon dioxide, and intriguing hints of dimethyl sulfide, a molecule on Earth primarily generated by biological processes. This detection remains tentative, requiring further observations for confirmation. However, if substantiated, it would represent the first potential biosignature detected in an exoplanet atmosphere. How does this discovery relate to 3I Atlas? The analytical techniques employed to scrutinize exoplanet atmospheres are directly applicable to the study of comet comas and jets. Spectroscopy, the process of dispersing light into its constituent wavelengths, reveals the molecules present. Whether examining a planet 40 parsecs away or a comet 2 astronomical units distant, the methodology remains consistent. We are living in an era where we can probe the atmospheres of distant worlds and dissect the chemistry of interstellar visitors. The tools employed are interconnected. The instruments that observe exoplanets during transits, when they pass in front of their host stars, can also be directed towards 3I Atlas to analyze its coma, jets, and any gases it may be emitting. The exoplanet findings from 2025 highlight the remarkable capabilities of modern astrochemistry. Decades ago, detecting exoplanets was a considerable challenge, let alone characterizing their atmospheres. Today, we are identifying individual molecules, assessing habitability, and searching for indications of life. This same analytical prowess is now being applied closer to home. 3I Atlas may offer a sample of extrasolar material, providing a direct glimpse into the chemistry of another star system. Its anomalous characteristics, including its acceleration, unusual coloration, and potential anti-tail, render it an unpredictable variable. If its composition proves to be exotic, rich in molecules not typically found in solar system comets, it will illuminate the diversity of planetary formation across the galaxy. The interdisciplinary nature of this research is striking. Planetary science, astronomy, instrumentation, chemistry, and physics all converge. The same scientists analyzing exoplanet spectra might collaborate with those studying 3I Atlas. The same telescope can serve both purposes. Let us consider a specific case study. The detection of water vapor and methane in K2-18b's atmosphere involved multiple observations of the planet as it transited its star. Each transit provided a spectrum illustrating which wavelengths of light were absorbed by the atmosphere. By comparing these spectra, astronomers identified absorption lines corresponding to specific molecules. The precision required is extraordinary, involving the detection of molecules present in parts per million within an atmosphere hundreds of trillions of kilometers away. Could analogous techniques reveal signatures of artificiality in 3I Atlas? It is possible. If the object possesses a metallic surface, engineered materials, or unusual reflectivity, spectroscopy might expose these features. Metals exhibit distinct spectral characteristics. A surface composed of aluminum or steel would reflect light differently than rock and ice. Polymers, ceramics, and other manufactured substances all leave discernible fingerprints in the spectrum. If 3I Atlas were a probe, a spacecraft of some kind, its surface materials could indicate its origin. Natural objects are composed of silicates, organic compounds, and ices. Artificial objects might incorporate alloys, composites, or coatings designed for durability in space. These distinctions should be detectable, provided we obtain high-resolution spectra. The same telescopes used to observe distant worlds can also be employed to scrutinize nearby interstellar intruders. JWST, Hubble, and ground-based observatories equipped with adaptive optics all contribute to this effort. The synergistic relationship between exoplanet science and solar system science is one of the less appreciated facets of contemporary astronomy. There is also a philosophical connection. The study of exoplanets is fundamentally about understanding our place in the cosmos and identifying other worlds that might potentially harbor life. The study of interstellar objects involves encountering fragments of those worlds, receiving visitors from systems we may never physically reach. Both pursuits are driven by the same fundamental question. Are we alone? If 3I Atlas is a natural phenomenon, it still acts as a messenger from another star, carrying information about its birthplace. If it is artificial, the implications are self-evident. In either scenario, it connects to the broader quest for life and intelligence beyond Earth. Next, we will examine recent discoveries in dark matter and modified gravity theories, which may offer insights into how we interpret anomalous accelerations observed in small bodies, like 3I Atlas. Part 12. New discoveries in dark matter or modified gravity. Earlier this year, astronomers unveiled findings from the Vera C. Rubin Observatory, which commenced operations in 2024. This observatory conducts the legacy survey of space and time, systematically imaging the entire southern celestial hemisphere every few nights. One of its primary objectives is to map the distribution of dark matter by observing galactic clustering and the bending of light around massive structures. A recent result indicated discrepancies in galactic rotation curves that do not entirely align with conventional dark matter models. Rotation curves illustrate the speed at which stars orbit the center of a galaxy at varying distances. In a galaxy composed solely of visible matter, stars farther from the center would orbit more slowly, in accordance with Kepler's laws. However, observations reveal that they orbit at comparable speeds to stars closer to the center, implying the presence of unseen mass. This invisible mass is termed dark matter. The new data from the Rubin Observatory suggests that the distribution of dark matter within certain galaxies is either more clumpy or more diffuse than theoretical models predicted. This could signify that our comprehension of dark matter is incomplete, or it might hint at the validity of modified gravity theories, alternatives to general relativity that account for galactic dynamics without positing unseen matter. The implications are far-reaching. Dark matter is theorized to constitute approximately 85% of all matter in the universe, yet it has never been directly observed. Its presence is inferred from gravitational effects, such as the rotation of galaxies, the bending of light around galaxy clusters, and the structure of the cosmic microwave background. However, its composition remains unknown. Decades of experiments searching for dark matter particles, specifically weakly interacting massive particles or WIMPs, have yielded no definitive results. Detectors, situated deep underground and shielded from cosmic radiation, await the collision of a dark matter particle with an atomic nucleus. To date, no conclusive detection has been made. The data from the Rubin Observatory introduces another layer of uncertainty. If the distribution of dark matter deviates from our models, it suggests we may be overlooking a fundamental aspect of its behavior. Or, a more radical possibility, dark matter might not exist at all, and gravity itself may operate differently on vast scales than we currently understand. Modified gravity theories, such as modified Newtonian dynamics, MOND, propose that Newtonian laws break down when gravitational acceleration becomes exceptionally weak, as is the case in the outer regions of galaxies. Instead of invoking unseen matter, these theories propose modifications to the equations of motion. While MOND has achieved some success in explaining galactic rotation curves without recourse to dark matter, it encounters difficulties with other observational data, such as gravitational lensing and the cosmic microwave background. The debate between dark matter proponents and advocates of modified gravity has persisted for decades. Most physicists favor the dark matter hypothesis because it better aligns with a broader range of observations and integrates more seamlessly with our understanding of particle physics and cosmology. However, the persistent lack of direct detection keeps modified gravity theories in contention. What is the connection to 3I Atlas? When we observe a non-gravitational acceleration in an object like 3I Atlas, we are operating under the assumption that our model of gravity is accurate. We calculate the object's predicted position based on the gravitational influence of the Sun, planets, and relativistic effects. Any deviation from this prediction is then categorized as non-gravitational, implying it originates from a source other than gravity. But what if our gravitational model is subtly flawed? What if there are minor corrections, unaccounted forces, or subtle effects that have yet to be discovered? In that case, what we interpret as thrust or outgassing might actually be a misinterpretation of the underlying physics. This is a remote possibility, but it warrants consideration. Historically, anomalies in orbital mechanics have paved the way for new physical theories. The precession of Mercury's orbit, the gradual rotation of its elliptical path, could not be adequately explained by Newtonian gravity. Einstein's general relativity provided a solution, demonstrating that the curvature of space-time near the Sun caused this effect. Could the anomalies observed in the trajectories of small bodies hint at a similar phenomenon? It is unlikely. The scales involved are different. Dark matter and modified gravity theories are relevant on galactic scales, where gravitational fields are weak and distances are immense. The inner solar system, where 3I Atlas is currently moving, is characterized by strong gravitational fields dominated by the Sun. Any corrections derived from modified gravity theories would be minuscule, far smaller than the observed acceleration. To illustrate, the gravitational acceleration at Earth's distance from the Sun is approximately 6 millimeters per second squared. At 3I Atlas's perihelion distance of roughly 1.4 astronomical units, this acceleration is even greater. Modified gravity theories predict deviations from Newtonian gravity when accelerations fall below approximately 1 times 10 to the negative 10th meters per second squared, which is 100 million times weaker than what 3I Atlas is experiencing. Therefore, any effect attributable to modified gravity would be utterly negligible in this context. Nevertheless, the recent findings in dark matter research serve as a reminder that our understanding of gravity and mass is not yet complete. We do not know the nature of dark matter. We have never directly detected a dark matter particle. Its existence is inferred from gravitational effects, but its fundamental nature remains elusive. The mystery deepens when considering the cosmological scale. The universe's expansion is accelerating, driven by an entity we refer to as dark energy. Like dark matter, its composition is unknown. It accounts for approximately 68% of the universe's energy density. Yet it is entirely invisible and detectable only through its gravitational influence. Consequently, roughly 95% of the universe, comprising dark matter and dark energy, consists of entities we do not understand. If our models of mass distribution are incomplete, could we be misinterpreting small force accelerations? Could factors such as radiation pressure, drag from the interplanetary medium, or interactions with the solar wind be more significant than we currently believe? These are natural forces that do not necessitate exotic physics, but their magnitudes might be underestimated. Sunlight exerts radiation pressure on objects in space. This effect is negligible for large, massive bodies, but can be considerable for small particles or objects with a large surface area relative to their mass. Astronomers account for this phenomenon when calculating orbits, but these calculations are contingent upon knowledge of the object's size, shape, and reflectivity. If these parameters are uncertain, the estimates of radiation pressure could be inaccurate. The Yarkovsky effect is another subtle force. When a rotating object absorbs sunlight, it heats up. The heated side then radiates this energy as infrared light, generating a minuscule thrust. Over time, this can measurably alter an object's orbit. Asteroids drift slowly inward or outward over millions of years due to the Yarkovsky effect. Again, astronomers model this, but it requires knowledge of the object's thermal properties, rotation rate, and surface composition. Drag from the interplanetary medium is even more subtle. Space is not a perfect vacuum. It contains a tenuous plasma of charged particles streaming outward from the Sun. Objects moving through this medium experience a tiny drag force from the solar wind. For most objects, this effect is negligible. However, for something as large and fast as 3I Atlas, could it be significant? The observed acceleration of 3I Atlas, approximately 0.02 millimeters per second squared, is exceedingly small. it lies at the threshold of what can be reliably measured. Minor systematic errors in astrometry, slight mismodeling of planetary perturbations, or unaccounted forces could mimic a non-gravitational acceleration. Astrometry, the precise measurement of an object's position in the sky, presents considerable challenges. It involves tracking a faint point of light against the backdrop of stars, attempting to pinpoint its location with fractions of an arcsecond. Atmospheric turbulence distorts images. Telescope imperfections introduce aberrations. Uncertainties in timing add noise. Even with the most sophisticated instruments, some degree of measurement error is inherent. When fitting an orbit to astrometric data, astronomers solve a complex equation that balances the gravitational forces exerted by the Sun, planets, and sometimes even large asteroids. If the measurements contain subtle systematic biases, if the timestamps are slightly inaccurate, or if the star catalog used for positional reference contains errors, the resultant fitted orbit will exhibit residuals. These residuals might appear as a non-gravitational acceleration, when in reality they are merely noise. That being said, astronomers exercise considerable care. They account for known forces, modeling solar radiation pressure, and the Yarkovsky effect, which generates a small thrust from absorbed sunlight. They also consider planetary gravity and relativistic effects. If they report a residual acceleration, it signifies that these known factors do not adequately explain the observation. The Jet Propulsion Laboratory and the Atacama Large Millimeter Array are world-class facilities, and the sources of the astrometric data cited by Avi Loeb are highly reputable. Their measurements are considered trustworthy. The 4 arcsecond discrepancy that Loeb mentioned is significant and well above the noise level. Therefore, the non-gravitational acceleration is likely genuine and not an artifact of faulty data. However, the interpretation of that acceleration, specifically its cause, remains open to question. Outgassing is the prevailing explanation. But, as we have discussed, this hypothesis necessitates a high rate of mass loss, which has not been definitively observed. Could there be another natural mechanism that we are overlooking? One possibility is fragmentation. If 3I Atlas is disintegrating, shedding pieces as it heats up, the ejected fragments carry momentum. This momentum transfer generates a reaction force that accelerates the main body. This process is analogous to outgassing, but is driven by mechanical breakup rather than sublimation. Comets occasionally fragment, particularly when subjected to tidal forces or rapid rotation. If 3I Atlas is a rubble pile, a loosely bound collection of rocks and ice held together primarily by gravity, it might be inherently unstable. Another potential explanation involves electrostatic effects. Objects in space can accumulate electric charge from the solar wind and cosmic rays. If the charge distribution is asymmetric, interactions with the interplanetary magnetic field could produce minor forces. This is a speculative hypothesis, and the effect would likely be very small, but it represents a natural mechanism that does not rely on outgassing or propulsion. The connection between 3I Atlas and dark matter is speculative, serving as a point of engagement for viewers to contemplate the boundary between established and unknown physics. Could an interstellar object harness some form of propulsion or react to an unknown ambient medium? If our models of gravity and mass are incomplete, could non-gravitational acceleration signify something different than we currently understand? Imagine the existence of a 5th fundamental force beyond gravity, electromagnetism, and the strong and weak nuclear forces. Physicists have actively searched for such fifth forces for decades, conducting precision experiments to ascertain whether gravity behaves precisely as predicted by general relativity. To date, no definitive deviations have been confirmed, but the possibility remains tantalizing, particularly in unexplored scales or regimes. An interstellar object like 3I Atlas, originating from a different environment, might interact with forces or fields not encountered in solar system objects. Its composition, forged in another star system under distinct conditions, might include elements or structures that respond to the interplanetary medium in unanticipated ways. These are provocative lines of inquiry, but they should not detract from more conventional explanations. Outgassing remains the leading hypothesis. The object is likely a comet exhibiting unusual characteristics rather than a manifestation of new physics. The elegance of scientific inquiry lies in its reliance on evidence rather than conjecture. Empirical data will serve as our arbiter. Should 3I Atlas exhibit all the characteristic markers of a comet, substantial gas expulsion, the presence of a coma, and spectroscopic indications of volatile compounds, then its observed acceleration is readily explained. Conversely, if these anomalies persist without a discernible natural mechanism, it compels us to entertain more unconventional hypotheses. The proposed linkage to dark matter or modified gravity theories is presently more conceptual than concrete, serving as a poignant reminder of the universe's inherent complexity and the incompleteness of our current cosmic understanding. We remain in a perpetual state of learning, discovery, and model refinement. Regardless of its ultimate classification, 3I Atlas represents a crucial data point in this ongoing scientific endeavor. We now shift our focus to the profound impact of artificial intelligence on orbital prediction and anomaly detection, which may illuminate the true nature of 3I Atlas. Part 13 delves into AI-driven astrometric orbit prediction tools. Artificial intelligence is revolutionizing our approach to cosmic exploration. Machine learning algorithms possess the capacity to process immense datasets, discern intricate patterns, identify deviations, and generate predictions with unparalleled speed and precision compared to conventional methodologies. In the year 2025, the introduction of several novel AI-powered tools for astrometry and orbit forecasting marked a significant advancement, and their influence is already palpable. A prime illustration is OrbNet, a sophisticated neural network developed through the collaborative efforts of academic institutions and space agencies. OrbNet assimilates astrometric data, observations detailing an object's positional changes over time, and contrasts them against a purely gravitational model. Its output includes residuals, which represent the discrepancies between observed and predicted positions, and it flags objects exhibiting substantial deviations. OrbNet underwent training utilizing decades of data pertaining to asteroids and comets, thereby learning to distinguish between normal celestial behavior and anomalies. When encountering an object like 3I Atlas, which displays measurable non-gravitational acceleration, OrbNet not only flags the anomaly, but also proposes potential underlying causes based on the patterns it has previously identified. These could include outgassing, fragmentation events, collisions, radiation pressure, or even an unidentified propulsive force. The significance of this lies in the potential for subtle trajectory deviations to be overlooked or inaccurately modeled by traditional methods. Human astronomers, when fitting orbits to observational data, might disregard minor residuals, attributing them to inherent noise. AI, however, with its ability to analyze thousands of parameters concurrently, can detect patterns that elude human observation. In the case of 3I Atlas, AI systems are diligently refining its orbital path, identifying minute propulsive vectors, and assisting in either refuting or substantiating hypothetical maneuvers. Should the object's acceleration fluctuate over time, vary with its proximity to the Sun, or exhibit directional characteristics inconsistent with outgassing, AI will reliably detect these phenomena. Another advanced tool, Astro-AI, was released by the European Space Agency this year. It employs reinforcement learning techniques to forecast the future trajectories of near-Earth objects and interstellar visitors. By training on historical data sets and simulating millions of potential paths, it can accurately estimate the magnitude of corrective maneuvers required to achieve specific objectives, such as aligning with a designated target. Researchers have already leveraged Astro-AI to scrutinize 3I Atlas. They input the observed acceleration, its current orbital parameters, and Earth's precise location. The AI then conducted simulations, posing the question of what velocity alteration, applied at what specific time, and in what precise direction, would result in an Earth intercept on December 19th. The AI's response was unequivocal. The necessary velocity change, or delta V, is substantially greater than 86 meters per second. Achieving such an intercept would necessitate several kilometers per second of applied velocity change months in advance, with exceptionally precise directional control. The assertion circulating on social media does not withstand rigorous modeling. This is precisely where AI demonstrates its remarkable capabilities. It can systematically explore a vast parameter space, evaluating thousands of potential scenarios within mere seconds. In contrast, a human astronomer might manually calculate only one or two scenarios. AI, however, computes all possibilities and identifies those that are physically tenable. Nevertheless, AI is not without its limitations. Its efficacy is intrinsically tied to the quality of its input data. If the astrometric observations suffer from systematic errors, or if the object's motion is more intricate than the model presumes, AI can yield misleading outcomes. It might flag non-existent anomalies, or fail to recognize subtle effects absent from its training data. Furthermore, AI can ascertain correlations, but not always definitively establish causation. It might observe a correlation between acceleration and solar distance, suggesting outgassing, but it cannot definitively identify the specific chemical processes driving this phenomenon. Such determinations necessitate spectroscopic analysis, imaging, and human expert interpretation. Consequently, AI's role in the investigation of 3I Atlas is primarily supportive, not conclusive. It aids in refining orbital calculations, identifying patterns, and ruling out improbable scenarios. However, the ultimate determination, whether the object is natural or artificial, a comet or a probe, rests upon observational evidence and rigorous scientific reasoning. There exists another crucial dimension to AI's application in astronomy: pattern recognition in radio signals. The ongoing search for extraterrestrial intelligence generates an overwhelming volume of data. Radio telescopes meticulously survey the cosmos, capturing signals across millions of distinct frequency channels. The vast majority of these detected signals are either background noise, human-generated interference, or naturally occurring astrophysical phenomena. Identifying a genuine technosignature, an artificial signal originating from an advanced civilization, is akin to locating a single grain of sand on an immense galactic beach. AI plays a vital role in this pursuit. Algorithms trained to discern patterns within noisy data can flag candidate signals for subsequent human analysis. They are adept at filtering out terrestrial interference, identifying frequency drifts indicative of a transmitter located on an orbiting or moving platform, and detecting modulation patterns that suggest the presence of encoded information. If 3I Atlas were indeed emitting radio signals, such as the purported 1.4 gigahertz pings mentioned in social media posts, AI would likely detect them. The absence of any reports from major observatories, despite continuous sky monitoring, provides strong evidence against the existence of such signals. AI is designed not to overlook such occurrences. Were there any structured radio emissions emanating from the object's direction, they would have been flagged, subjected to analysis, and either confirmed or definitively identified as interference. Therefore, the projections derived from AI-driven orbital analysis suggest that by late 2025 and early 2026, we will possess definitive updates regarding 3I Atlas's trajectory. Residuals will be quantified with exceptional precision. Any persistent acceleration will be meticulously mapped in 3 dimensions. Temporal correlations with solar distance, rotational periods, or other relevant factors will be identified. And the hypothesis of a deliberate maneuver, the assertion that it is steering towards Earth, will be either confidently validated or conclusively refuted. The inherent transparency of AI tools also contributes to public trust. The results generated by these systems can be independently reproduced, scrutinized, and verified by researchers worldwide. Unlike proprietary models or closed-door calculations, open-source AI platforms empower anyone with access to the data to conduct their own analyses. This process democratizes scientific inquiry, making it significantly more challenging for misinformation to gain traction. We now transition to advancements in radio astronomy, particularly focusing on the 1.44 GHz band and its implications for detecting potential technosignatures from objects like 3I Atlas. Part 14 examines breakthroughs in deep space radio astronomy at 1.4 GHz and beyond. The field of radio astronomy has experienced a remarkable year. In early 2025, the Breakthrough Listen project, a prominent initiative dedicated to the search for technosignatures, released findings from a comprehensive survey encompassing millions of stars within the 1.2 to 1.8 GHz frequency range. This spectrum includes the 1.4 GHz hydrogen line, a natural frequency considered a prime candidate for interstellar communication. The survey yielded no confirmed technosignatures, but it established stringent limitations. If advanced civilizations were broadcasting powerful radio signals at 1.4 GHz within a few thousand light-years of Earth, they would have been detected. This observed silence is profoundly informative, suggesting either that intelligent civilizations are exceedingly rare, that they do not broadcast within this specific frequency band, that their signals are too attenuated for our current detection capabilities, or that they are intentionally remaining silent. Significant progress in signal processing, the deployment of larger antenna arrays, and AI-powered filtering have rendered radio astronomy more sensitive than ever before. Facilities such as the Meerkat Array in South Africa, the Very Large Array in New Mexico, and the soon-to-be-completed Square Kilometer Array will further enhance detection capabilities. We are entering an era where detecting faint radio emissions from nearby stars or transiting objects is not only feasible, but becoming routine. This brings us to the social media claims concerning purported 1.4 GHz pings originating from 3I Atlas. These claims suggest that the object emitted structured signals in proximity to Mars, possibly as forms of communication for navigational adjustments or greetings. The specific choice of 1.4 GHz is noteworthy. This frequency falls within the water hole, a remarkably quiet segment of the radio spectrum characterized by minimal galactic background noise, allowing signals to propagate with exceptional efficiency. If an advanced civilization intended to transmit a signal detectable by others, the 1.4 GHz frequency would represent a logical and universal choice, as the hydrogen line is consistent throughout the universe, readily recognizable by any civilization possessing radio astronomy capabilities. However, the critical issue is the absence of any publicly available peer-reviewed detection of such signals, originating from 3I Atlas. Radio telescopes continuously monitor the celestial sphere, and projects like Breakthrough Listen are specifically designed to identify transient signals, bursts, and anomalies. If 3I Atlas were emitting 1.4 GHz pings with sufficient intensity to be detected on Earth or in the vicinity of Mars, it would have been observed. Could the signals have been too weak? This is a possibility. Radio signal strength attenuates with distance according to the inverse square law. At a distance of 1 or 2 astronomical units, a low-power transmitter might fall below detection thresholds, but then it would similarly be undetectable near Mars, the location cited in the social media reports for the purported pings. Could the signals have been intermittent, brief bursts that were missed? This is also a plausible scenario. Radio observations are not continuous. Telescopes have limited observing time and are not always precisely oriented towards the target at the opportune moment. A short-duration burst could potentially evade detection. However, the lack of any independent corroboration is a significant red flag. If these pings were indeed real, multiple observatories should have registered them by now. The fact that none have suggests the claim lacks substantiation. Let us now consider the plausibility of these claims from an engineering perspective. Assuming 3I Atlas is an artificial probe, what would be required to transmit a 1.4 GHz signal detectable across interplanetary distances? Radio transmission necessitates both power and an antenna. The required power output depends on the transmitter's design and its energy source. The efficiency of an antenna is determined by its size and the wavelength of the signal. At 1.4 GHz, the wavelength is approximately 21 centimeters. A reasonably efficient antenna would likely measure a few meters in diameter, a size that could realistically be accommodated on a spacecraft. If the probe possesses a nuclear power source or another long-term energy supply, generating a few watts or kilowatts of radio power would be technically feasible. This output would be sufficient for detection at distances of millions of kilometers, provided a sensitive receiver and a directional antenna are employed. However, natural phenomena can also produce radio emissions. Comets, through their interaction with the solar wind, can induce plasma instabilities that generate radio waves. Lightning and dust clouds, if present, could also result in broadband radio bursts. While these events are infrequent, they are not impossible. Therefore, even if a radio signal were detected from 3I Atlas, it would not automatically confirm the object's artificial origin. A thorough analysis of the signal's structure would be imperative, searching for modulation patterns, repetition, frequency drifts, or any characteristics that indicate the presence of information rather than random noise. What should we be observing in the coming weeks? Upcoming radio astronomy observation campaigns are specifically targeting the region around 3I Atlas. Multiple observatories are coordinating their efforts, covering various frequency bands and observation times. Data release schedules are anticipated to provide results by late 2025 or early 2026. SETI organizations are also actively monitoring the situation. Breakthrough. LISTEN has added 3I Atlas to its observation targets. If any anomalies exist within the radio spectrum, they are likely to be identified. Radio astronomy's critical role in this investigation is to either validate or definitively refute the techno-signature hypothesis. If no signals are detected despite comprehensive monitoring, the claim will be dismissed. Conversely, if signals are detected and independently verified, the entire discourse will shift dramatically. Radio astronomy also serves as a powerful tool for debunking unsubstantiated claims. Numerous purported anomalies, ranging from fast radio bursts initially suspected to be alien transmissions to enigmatic pulses later revealed to be microwave ovens operating within the observatory cafeteria, have ultimately been attributed to natural or human-made sources. The scientific community in this field maintains a strong ethos of skepticism and rigorous verification. Whether 3I Atlas proves to be a natural phenomenon or an engineered artifact, radio astronomy stands as a frontier technology for discovery. For the present, the silence emanating from the object speaks more profoundly than any alleged pings. We now conclude our investigation, summarizing our findings and outlining the anticipated developments in late 2025 and early 2026. Part 15 provides a summary and looks ahead to future developments in late 2025 and early 2026. Let us synthesize the information gathered. Our investigation commenced with a dramatic assertion that 3I Atlas might be strategically aligning itself with Earth. This claim was predicated on verifiable data, a reported non-gravitational acceleration of 0.02 millimeters per second squared, and a straightforward calculation demonstrating that 50 days of such acceleration could theoretically result in a velocity change of 86 meters per second. The arithmetic is indeed sound, and the underlying data are authentic. However, the extrapolation of this finding, the leap from the mere existence of acceleration to the conclusion of Earth-directed targeting, relies on assumptions that remain unverified. Such an acceleration would need to be sustained, precisely directed, and coincident with Earth's orbital position at an exact moment. None of these critical conditions have been established. We have examined the object's trajectory and its predicted misdistance. Official sources indicate that 3I Atlas will pass Earth at an approximate distance of 1.88 astronomical units, equivalent to about 270 million kilometers, on December 19, 2025. This is an immense distance, far beyond any plausible impact scenario. To achieve an intercept, a significantly greater velocity change would be required, applied over a more extended period with meticulous timing. The current data simply do not support the assertion of an Earth alignment. We have thoroughly explored potential natural explanations for the observed acceleration. Outgassing, the process of ices sublimating to create thrust, remains the primary hypothesis. However, the required rate of mass loss is substantial, potentially amounting to 1/16 of the object's total mass within a month. If Avi Loeb's calculations hold true, this level of mass expulsion should produce a prominent coma, a phenomenon that has not yet been definitively observed by our telescopes. The scientific community awaits further conclusive evidence on this matter. We have also considered more unconventional hypotheses. Could 3I Atlas be an artificial construct, a probe dispatched by an extraterrestrial civilization? The observed acceleration, its estimated size, and its trajectory all contribute to raising these questions. Nevertheless, there is no conclusive evidence, no definitive smoking gun, no detected radio signals, no signatures of non-volatile propulsion, no irrefutable proof. The hypothesis remains speculative, intriguing, but as yet unverified. The narrative disseminated through social media amplified the initial claim, transforming a scientific anomaly into a sensationalized account of alien interception. This narrative disseminated far more rapidly than the scientific explanation, blurring the lines between empirical data and speculative interpretation. It serves as a potent reminder of information dissemination in the contemporary era, illustrating how uncertainty can be transmuted into spectacle, and how human pattern-seeking tendencies can readily populate informational voids with dramatic conjecture. We have also considered the implications of a worst-case scenario. If the object were to, against all odds, intercept Earth, the consequences would be catastrophic, potentially an extinction-level event. However, the chain of assumptions required to reach such a conclusion is exceptionally long and inherently fragile. The object would need to possess capabilities, intent, and a precisely timed trajectory that approach implausibility. Furthermore, we have broadened our perspective, situating the investigation of 3I Atlas within the context of broader advancements in space science. Progress in exoplanet atmosphere imaging, research into dark matter, the development of AI-driven orbit prediction tools, and sophisticated radio astronomy techniques all contribute to a more comprehensive understanding. This inquiry transcends the examination of a single object. It delves into the fundamental methodologies we employ to study the universe, detect anomalies, interpret complex data, and prepare for the unforeseen. Therefore, what are the principal conclusions to be drawn? Firstly, 3I Atlas represents a rare interstellar visitor, possessing significant scientific value irrespective of whether its origin is natural or artificial. Secondly, the mathematical basis for the 86 meters per second velocity change calculation is accurate. However, it does not inherently imply an Earth impact. Thirdly, critical unknowns persist. These include the precise vector of the observed acceleration, whether this acceleration is sustained, and its temporal alignment with Earth's orbital path. Fourthly, forthcoming observations scheduled for late 2025 are of paramount importance. Data concerning mass loss, astrometric residuals, spectroscopic analysis, and radio monitoring will collectively elucidate the object's true nature. Fifthly, while worst-case scenarios may appear dramatic, they are contingent upon numerous unverified assumptions, and official agencies have indicated no perceived threat. Sixthly, diverse scientific disciplines converge on the study of 3I Atlas, rendering it a focal point for multiple avenues of inquiry. Let us consider the timeline of events. The object reached its perihelion, its closest point to the Sun, around October 30th. It has now passed this point and is proceeding outwards. November marks the intensification of observation campaigns, as the object emerges from the sun's glare, becoming more readily observable. December 19th, 2025, is designated as the date of its closest approach to Earth, the critical juncture highlighted in the social media claims. By this date, we will have accumulated several weeks of additional observational data. Early 2026 will witness the object's outbound trajectory, with a potential distant flyby of Jupiter scheduled around March. Subsequently, 3I Atlas will recede from view, venturing deeper into the outer solar system, and eventually returning to interstellar space. What aspects should you be attentive to? Seek out official orbit updates from NASA, ESA, and other prominent space agencies. Pay close attention to refined calculations of the missed distance and any adjustments to the predicted trajectory. Monitor spectroscopy results closely. Are volatile compounds being detected? Is a coma forming? Does the object's color continue to exhibit unusual characteristics? Observe imaging reports. High-resolution photographs from observatories like the Hubble Space Telescope or the James Webb Space Telescope may reveal surface features, active jets, or other discernible structures. Keep abreast of announcements from radio telescope facilities. Any detection of signals in the 1.4 GHz band or other frequencies would constitute monumental news. Furthermore, observe the divergence between media narratives and official scientific statements. How do mainstream news outlets frame the story? Do they emphasize caution or sensationalism? How do scientists address and respond to the claims circulating on social media? This dynamic interplay between public perception and scientific rigor is an integral part of the unfolding narrative. If no significant developments emerge by early 2026, what conclusions can be drawn? Does this definitively invalidate the maneuver hypothesis? Almost certainly. If the object behaves as a typical comet, exhibiting predictable outgassing that diminishes as it moves away from the sun, if its acceleration ceases or decreases, and if no radio signals are detected, then the natural explanation will prevail. In such a scenario, 3I Atlas would join the ranks of other scientifically interesting, yet ultimately conventional, interstellar visitors. However, should anomalies persist, if the acceleration continues unabated far from the sun, if mass loss remains minimal despite the observed thrust, or if radio signals are indeed detected, then we face a genuine scientific enigma. In such an event, the more speculative hypotheses would cease to be mere conjecture and would demand rigorous scientific investigation. Will 3I Atlas settle into the category of an interesting but natural celestial body, or will it be recognized as the first confirmed engineered interstellar probe? The answer will not be derived from social media speculation, but from the painstaking work of scientists utilizing telescopes, analyzing data, and interpreting evidence with meticulous care. One final consideration: the universe does not conform to our expectations for comfort. It is indifferent to our readiness for its revelations. For centuries, humanity has progressively recognized its less central, less unique position in the cosmos, gradually shedding anthropocentric perspectives. Every significant scientific discovery has contributed to a growing sense of humility. 3I Atlas, irrespective of its ultimate classification, represents another step on this evolutionary journey of understanding. If it proves to be a comet, our knowledge of the diversity of interstellar travelers will expand. If it is something else entirely, it will signify that the galaxy is far more complex and potentially more populated than we currently imagine. In either outcome, the object serves as a powerful reminder to look upwards, to maintain our curiosity, to pose critical questions, and to remain prepared for possibilities that lie beyond our current imaginings. The investigation is far from over. Indeed, it is only just commencing. The coming months will determine whether the social media claims were flights of fancy or precursors to a more extraordinary unfolding of events. By early 2026, we will have a clearer answer. Until then, continue to observe the skies. The universe is observing us in return.